So what we're going to talk about today is linear regression, which we've already kind of talked about in some sense when we talked about curve fitting on the very first lecture, right? So here I want to talk a little bit more specifically about linear regression and a couple of kind of variations on the theme, right? So linear regression. And this is like the most basic machine learning problem that there is, basically, right? So the idea is that we have n observations, each in d dimensions. And I'm going to think about these as a vector, x1, or I'm going to think about this as a set of observations, x1 through xn, and then each xi is actually a vector of data, right? xi dimension 1, xi dimension 2, ... xi dimension d. And usually I try to think about these as column vectors, and I try to keep that notation throughout. Depending on what we're doing, I may find myself switching back and forth between row and column vectors. Hopefully it's clear from context, okay? And then for each of these observations, we have a target variable that we're trying to predict. So for each observation, we also have a target variable, or a target value. Let's call it t sub I, okay? And this target is a continuous real-valued number, okay? Remember, regression is what you're doing when you're predicting a real-valued number, and classification is what you're doing if you're predicting a label, right? So for today, we're sticking with predicting a number, okay? And so what we want to do is we want to build a model that predicts t from the x's according to some sort of function of the x's, right? And so this function is going to be given by what we call y. So we want to build a model, let's call it y of x, to predict the value of t. Okay? And the simplest model is just a linear model, right? So that's, simplest, the simplest model function is just a linear function that says my prediction at a given x is a constant term plus some number times the first dimension of x plus some number times the second dimension of x all the way out to some number times the dth dimension of x. Okay? And a different way of writing this would be to say, w0 plus some weight vector transpose x, right? Now, we give these, I said the word weight vector, right? So basically, typically the things that multiply, the x's, we call weights. And the constant term sometimes has a separate name that you call the bias. And it's a little bit confusing because we're going to talk about a different way of using the word bias even just later in today's lecture, right? But generally, in the context of a linear problem, bias is the constant term and weights are the things that multiply the x's, okay? And so that's kind of what okay, so this is like the most basic thing, right? Straight line, more or less. Now, this is a little bit constraining, right? Because we already know that there may not be a direct linear relationship between the variables and the thing we want to predict, right? So we need a more general model than this, okay? So we're going to kind of change it up and say, more generally, our linear regression model looks like this. The model is, again, some bias term plus the sum, and I'm just going to have this over m-1 for the moment, of some weights times some functions. So this function phi is a new thing, right? So here, this phi of j is something that takes the d-dimensional feature x and turns that into a number. Okay? And so here, the way I've set this up, we have capital M total parameters, right? The bias plus m minus 1 weights. So we have kind of like, m total parameters to learn. And sometimes what we do is we lump the bias into the weights just to make it easy, right? So for example, one very simple phi function that doesn't actually depend on the values of x is just 1, right? So if I map one of those basis functions or one of those phis to 1, then I can kind of just have a sum, right? So sometimes we let, kind of like phi 0 of x just equal 1, and then incorporate the bias term into the weights. And I already said this word. So these things, these phis, are what we call basis functions. And the basis functions themselves can be nonlinear, right? And we're going to talk about examples, but you already did this in curve fitting, right? So if I use x squared, x cubed, those are not linear functions. But the key thing is that the model is linear in the parameters w, right? So it's still a linear problem, even if I'm doing some sort of nonlinear transformations of the input variables, right? So that's a key idea, is that these functions can be nonlinear functions of x, but the model is still linear in the parameters w. So the way I think about the basis functions is a way of transforming the data in a way that is more predictive for the problem that we actually have, right? It's like changing the feature space. So, or it's like changing the coordinate system, right? So if you did calculus, right, you definitely learned how to convert from Cartesian coordinates to polar coordinates, right? That's a change from two variables to two other variables that often are easier to talk about if you're talking about the distance from an object. Then the radius is a more natural thing than the square root of x squared plus y squared, right? So we could kind of think about this as a transformation that changes the variables, right? And so, for example, what could we use for these phi functions, right? So, example basis functions. So, if we only have one dimension of x, right? So if there's only like, one x to every t value, then we could use what's called the polynomial basis, right? So we could say, x squared, x cubed, x to some power m is, like kind of like a Taylor expansion in a way, right, of a function. So what we're doing is we're finding coefficients on the polynomial values, and in fact, that's kind of what you did on homework 1. And also, if I had more dimensions than just one dimension of x, then it would be like the last part of the first homework problem, where you had like 3 dimensions and you looked at all the combinations of things, right? So basically, any products of these input variables would be like a polynomial basis, okay? Another one, if you are an electrical engineer, which I think many or most of you are, is what you call the Fourier basis, right? So in signal systems, you learned about how to take a signal and decompose it into, a constant plus something times a slowly varying sinusoid plus something times a sinusoid that varies a little bit faster, and so on, right? So basically, like you had like an A0 term times this, an A1 term, and an A2 term, and so on, right? That's just a different way of thinking about the same signal using different numbers, right? So you can imagine that we could take the input variable, we could have cosines and sines, and that would be a different way of representing the data, right? If you're kind of a more advanced signal processor, you may have heard of what's called the wavelet basis, right? So like the more advanced image compression algorithms use this thing called wavelets. And so wavelets are also a different way of thinking about, how to transform a function. I'm not going to talk about exactly what the structure of those wavelets is, but you kind of can look it up. Another one that we often see in machine learning is what are called radial basis functions. That's like saying that the basis function is like some function of the distance between the point x and some other point in the plane mu, right? So like that's like saying, okay, I have some point mu, and my function is related to this distance, which sometimes we call this r because it's like the radius I am away from mu, right? So if I call this r, then, for example, we could say that I could have the function be the radius squared, or I could have it be the radius squared times the log of the radius. That's for something called thin plate splines. I'll talk about that if I have time at the end of this lecture. Or you could have like a Gaussian function that says, e to the minus r squared over 2 sigma squared, right? Like a Gaussian function that says how far am I away, kind of as if there was a Gaussian centered at that point, right? And so that's a very different way of thinking about how I could map the input data to some other things, right? No matter what I do, the basis functions kind of form what I would call a feature vector of the input data, okay? And now I'm trying to find the best linear weights on this feature vector. Okay, so that's the setup. Questions or comments about anything I said so far? Okay, so now how are we going to find the best weights? Or basically, let's first of all think about what do we mean by the best weights, right? So we have a model that says that the observations that we see, the x comma t pairs, are coming from some true underlying, consistent model, right? Otherwise, what would be the point of trying to fit it, right? But we know we don't get exactly the answers that the underlying model predicts. Otherwise, there would be no problem in fitting the parameters. There's always some sort of noise, some sort of error in the observations that just comes from the fact that we probably have a lot of other things that we can't actually take account of about how the data was generated, right? So our model is that the target variables are related to the inputs by some true underlying function plus some sort of noise, right? That's like saying that the t that I want is like some true, something that I could truly model, right? Plus some epsilon, right? And that epsilon is the part that I can't actually know, right? So usually what we do is we model this thing as zero mean, Gaussian, IID, variance sigma squared noise, just like your standard kind of noise, okay? And that means now we can kind of solve this problem with a probability hat on, right? That's like saying that I can model the probability density of t conditioned on the input variables, some set of parameters, and the sigma squared of the noise, right? That's like saying, well, if I told you W, then the, this is like a normal distribution of this number centered around some true mean value, and I have sigma squared. So it's like saying the mean of this normal distribution is the truth, and then I have a Gaussian distribution around that given by whatever the variance of my noise is, okay? So now I need to figure out, okay, so how can I find the, now I see, n observations, and I want to find the best values of the weights, right? That is what we call maximum likelihood estimation, which we talked about a couple times already, right? And so far I'm not really actually saying anything that isn't already in your notes that we didn't already talk about, but I'm just kind of going it over again with a little bit of a different flavor, okay? So now we see many measurements. So now we see n observations, which we assume to be, again, all identically and independently distributed, IID. And we want to find the maximum likelihood estimate. Right? That's like saying what values of the W's maximize the corresponding likelihood of seeing them, okay? And so let's kind of expand this out over the n observations, right? So that's like saying that I have a PDF over this whole vector of targets, and then I have conditioned on, the set of n input vectors and my W and my sigma squared. And under the IID assumption, that's like saying, well, I can kind of, the joint distribution of these, I can take it apart into the smaller distributions, right? So I can say this is actually the product of a bunch of normal distributions for each of the targets given the model and sigma squared. And again, since we're doing linear regression, our model is like saying I take the weight and I transpose it times the set of basis functions, right? So it's like saying I have, the weights, W1 through Wm, and I'm multiplying that times the phi 1 at xn through the phi m at xn. That's what this is, right? And now, we have to remember that what we typically do is we look at the log likelihood as opposed to the actual likelihood, because the log likelihood is got the same maximizer and minimizer, and it's easier to work with in terms of math, right? So, taking the log likelihood, now what I'm going to do is I'm going to expand out what is this Gaussian distribution. So the log of this probability is the product becomes a sum, right? The sum from n equals 1 to n of the log of the Gaussian PDF. And the Gaussian PDF is, 1 over square root of 2 pi sigma e to the minus 1/2 sigma squared times, x minus the mean squared. And here, that's playing the role of the model, right? So I'm just kind of plugging in what do I know about the mean. The mean is this, basically, right? I guess need a big closing parentheses. And now I can take apart this log with the properties of logs. So now I can say this is equal to, the sum. I have a bunch of constant terms, don't really matter, right? I've got like minus 1/2 log of 2 pi minus log of sigma. And then I've got minus 1 over 2 sigma squared, target value minus this thing here. And again, since I have basically n of these measurements, there's going to be n times, this first part. There's going to be n times this log of sigma. And then I'm going to have, the sum of 1 over 2 sigma squared times this. And what this all comes down to at the end of the day is that this thing here is nothing more than the sum of squared error function. So certainly we said, I don't remember whether we proved it, but basically what this is telling us is that, minimizing the sum of squared errors is basically the same thing as the maximum likelihood estimate under the hypothesis that the errors are Gaussian distributed, right? So really, this comes down to minimizing this thing, okay? Which is something that we already know how to do. So that's something that we kind of learned about in the curve fitting lecture, right? If we have a bunch of measurements and we have a bunch of basis functions, in the homework, the basis functions were polynomials, but in this case, they could be anything. How do we do that? Well, we're going to solve a big linear least squares problem that comes down to solving a linear system like ax equals b, right? So what is that linear system, right? So we're going to take, how do I minimize this? I take the gradient with respect to the parameters, the gradient with respect to w, and I set that gradient equal to 0, right? We know from last time, that's what we kind of talked about, the gradient descent. We're trying to find the place where the gradient is exactly 0, right? So to minimize, we take the gradient of the log likelihood, and we set that equal to 0, right? With respect to w, the only thing we care about are these numbers w. And so this constant stuff doesn't matter. This sigma squared in front of here doesn't matter. All we really care about is, what is the derivative or what is the gradient of this, right? So that gradient is like saying, okay, I have the sum. Let's forget about the 2 sigma squared. So again, this here is a scalar. We're taking the gradient of that, so we're going to end up with a vector, right? And we can already know that when I take the derivative of this scalar with respect to this vector to get the gradient, it's just going to be these numbers at the end, right? So this 2 is going to come down and cancel out with this 1/2. So I'm going to get something like this. I'm going to get T of n minus W transpose phi of n times this thing here, right? And I'm going to set that equal to 0. Okay. And if I start to kind of move stuff around, what I get is the following, right? So if I move stuff around, what I get is that I've got the sum of, a matrix that comes from, actually, let me write it like this. I've got a matrix that looks like the sum of a bunch of outer products like this times W, and that equals the sum of these vectors times Tn. So again, if this is like a little bit like where are these transposes and so on coming from, take a look, work it out yourself with some simple matrices, and you can convince yourself that this is kind of what happens. The key thing to look at here is that this is like, some matrix times W equals some vector, right? We know how to solve that problem with linear least squares regression, right? That means I have this pseudo-inverse of this matrix, and I multiply that by this vector. So now what I'm going to do to kind of simplify my notation is I'm going to collect a bunch of junk together to make life a little bit easier, right? So this big matrix, what is this big matrix? So the key element is what we call the design matrix. N rows, M columns. And I'm going to give that kind of like a, capital phi with some extra bars like this. This is like saying what I do is I have, let's see how I want to write this here. I basically have, the phi functions. And here what I'm going to do is I'm going to include the bias. So I just have like m generic basis functions, which could include the bias. Oops. Right, so this is like saying I have, on this axis, I have n observations going down the rows. And then across the columns, I have m basis functions. And so I could think about this as like a different way of writing this matrix is like saying I have phi j of xn, right? Going down this way and going down that way. Okay. And so if I want to make my kind of more crappy looking equation here a little bit simpler looking, it turns out that we can kind of write them in the form of this matrix, right? So what we find out is that this equation system that we have to solve are called the normal equations. For the least squares problem. Are basically I have this design matrix. So I have this thing times this thing times t. So again, let's kind of do a quick dimension check, right? So this here, this phi is n by m, right? So that means that this whole thing is an m by m matrix. I know that the parameters I want to estimate are an m by 1 vector. This thing, again, is the transpose of this is an m by n matrix. This is an n by 1 vector. So again, this here is also an m by 1 vector. So now what I have is basically a square system that I can solve. And thus, the maximum likelihood estimate is taking the inverse of this matrix and bringing it over here. And you may remember that we called this thing here the pseudo-inverse of the phi matrix. And that's exactly what you did already, right? That's kind of what we were talking about in the very first mathy lecture, was forming up these normal equations in the specific case of a phi matrix that had powers of x along the columns, right? Here we're just doing it in a generic way, so the columns of this matrix could be all sorts of basis functions, okay? And so once I've got the weights, in a similar way, if I wanted to also figure out, in hindsight, what was the maximum likelihood estimate of the noise variance, like how much noise do I have in my observations, well, then in a similar way, the maximum likelihood estimate of the sigma is just saying, okay, now I've got my model, and I sum up the sum of squares difference of what I get by applying the maximum likelihood estimate, right? So here, this is basically the ML estimate of the noise variance, which I don't know, right? Okay, so nothing really new here, just in slightly a different form than maybe you're used to seeing it from before. So questions or comments about what I did here? Yeah?
What's the symbol of error for the equation for that next time?
This one, phi. Phi. So this phi basically is this big matrix here, right? It's like saying I apply the basis functions to each of the observations in turn. So I have this big matrix full of numbers, this scalar set of numbers, and I'm going to call that big capital phi, right? That collects all of my basis functions for all of my data. Okay? So again, let me just kind of, remember that for your curve fitting, right? For your curve fitting, you made a matrix that looked like, 1 x1 squared, x2 squared, dot, 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 1 xn squared, or xn, 1 x1, x1 squared, like this, right? So if I was fitting like a quadratic function to some points, I would build this, n by 3 matrix that contained the polynomial terms for each of my observations, right? So you already did this, in code. This is the more general version of that, right? Where these phi's could be radial basis functions or Fourier series or whatever you want, right? Now I will say, just kind of like as a preview, we will continue this kind of formalism of this idea of that these phi functions came from somewhere. They came from you, the user, right? You chose what to use, right? Now in practice, you may not know what would make good features for your data, and in some sense, that's what neural networks are a way of addressing, is implicitly defining basis functions in a way that you don't have to actually, figure it all out, right? The neural network kind of figures out what the basis functions should be for you. So that's kind of a preview of where we're going. But just for the moment, we're going to assume that these phi functions are out there. Now, the other thing I wanted to tell you is that, again, if you take a linear algebra class, which I totally recommend, there is a more geometric way of kind of thinking about what's going on, right? So let me just say that. So this is kind of like saying that I imagine that I have a generic space here, and this is basically the, set of all the things I can get, the subspace spanned by the basis functions, right? For example, that could be, all of my quadratic, functions if I'm fitting a parabola to a curve, right? Now, what I do is I observe some observation, right? This t is my observation, and it's not in the subspace. It's not in the subspace because there's noise, right? So this is like not in subspace because of noise. And what I want to do is I want to project that t down onto the subspace so that the error that I make, the difference between the projection and the t, is as small as possible, right? So kind of what I want to do is I want to build a right triangle down here so that, if I kind of build it like this, so here, this number here is, the best that I can do, right? This is like the linear combination of basis vectors or basis functions closest to t. And so if you kind of think about things in a geometry kind of way and you actually figure out, well, what is the length of that perpendicular line, it turns out that that's exactly the same set of equations that we derived in a non-geometric way, right? But this is a good way of thinking about it. It's like saying, I'm somewhere outside of the subspace. I want to come down and get the closest projection that I can, right? And this is as good as I can do, okay? Okay. So, questions, comments? All right, so one thing we talked about also was this idea of regularization, right? So one thing that I didn't introduce here at all was any sort of opinion about what these parameters should be, right? And in practice, we may have some sense of what the parameters should be, or we may have some sort of a general big picture that, I don't want to have too many parameters or something like that. So that's why we sometimes want to regularize our answer. So before, we talked about regularization, and we will also say more about this in future lectures, which has an error function of the form, the same error function I had before. This is my usual least squares error function. right? This is the usual data minus model errors. And then I can add to that, for example, something like this. So maybe I should be clear. This is only one way of regularizing. So I say, regularization, one form of which has this error function. That's probably more accurate, right? And so this lambda is tuned in such a way to encourage the W numbers to be small, right? And hopefully you discovered that on homework 1, right, where you basically turned up that lambda value and you found that your curves got flatter because the W numbers were getting pushed towards 0, right? And so this lambda is a, parameter tuned by the user to encourage sometimes what's called shrinkage. Which is basically a fancy way of saying weights tending towards 0. And, hopefully you already saw on your derivations in the homework that this can also be solved in exactly the same way as that other linear least squares problem, where the W star would be the same, phi transpose phi inverse, but now there's an extra term here that hopefully you remember is like this lambda I, right? So again, this here is like the, M by M identity matrix. Right, so this is something that, a different way of thinking about this, if we were going to take a more Bayesian approach, would be to say that, this is like a prior on what we expect the W values to be. We expect them to be small, right? And so we're pushing the W values in the direction of the prior, while also compensating for the evidence, which is what we actually see in the observations, right? But like I said, this is not the only way to do it, right? So there are more general ways of doing regularization, which I may or may not touch on in more detail, but this is a specific one that says that the sum of squares of W should be small, right? Another way of doing that is to say, another way, another way of doing regularization, which you may see if you're reading an academic paper, is called the lasso, which sounds cool. And it's basically the same, 1/2 sum of squares, but instead I have a regularization parameter times basically the sum of the absolute values of W, right? So instead of the sum of squares, I look at the, 1 norm or absolute value of these numbers. So this is still a way of encouraging the W's to get small, but it has an added kind of benefit, as it turns out, of not only trying to make the W's small, but also trying to make the W's what's called sparse, right? Which means that I'm trying to push some W's right onto 0 and other W's are non-zero, right? So if you're looking for something where the model is controlled by a relatively small number of weights, then maybe you want to apply this type of regularization instead, right? Because the result is that as lambda gets big, this leads to W star being what's called sparse, which means that, some parameters are exactly 0. And, there are some reasons for that you may want. So again, whenever you're doing regularization, you're not getting the maximum likelihood estimate anymore because you are now kind of pushing your estimate in a direction that's not quite exactly what the data tells you. You're having some external information that is moving your estimate around, right? So that's something to kind of keep in mind, is that I'm not calling this the maximum likely estimate. I'm just calling it the optimal estimate according to whatever cost function that I set. Okay. Okay. So I felt like I spent like half the lecture telling you stuff. Oh, question.
I'm kind of curious with the lasso, so kind of like how it basically, kind of like how it's better than.
So the better part of the lasso is the sparsity aspect, right? So if I'm encouraging like the sum of squares of W to be small, then I could just get like a whole bunch of very small numbers, right? But they're not exactly 0, right? If I use this one norm regularization instead, then that will push some of the W's to be exactly 0 and the other W's to be small, right? So that exactly 0 aspect is what's beneficial, because in some sense it says that weight on that basis function is totally thrown away. Like that basis function doesn't contribute at all, as opposed to that basis function contributing like 0.0001, right? So there may be some benefit to doing that. It makes your model more compact, right, is one way of thinking about it. Okay, so let's talk about something that's totally, that you haven't heard before, right? So I think everything that I said so far is really not that different than curve fitting, right? But there's one kind of key, like machine learning theory result that I want to talk to now, right? And that's called, just sort of saying it, it's called the bias variance trade-off, right? So we talked about overfitting and underfitting, right? And I want to kind of come back to that in a little more of a formal way, right? So remember, overfitting and underfitting. And if you don't remember what those mean, I'm going to say it again in this lecture anyway. So these can be kind of captured by what's called the bias variance trade-off. And I feel bad about using the word bias twice in different ways in this lecture. This bias is not the same as the constant term bias, but I'll define what I mean here, okay? So let's think about this kind of toy problem, right? So here, let's suppose that the truth is a quadratic function, okay? So I don't have that many colors, but I'll stick with black for the moment. So let's suppose that the truth is some parabola, right? And then let's suppose that, so let's call this H star, okay? So now let's suppose that I see data points that are the truth plus noise, okay? So let's suppose that my, and I feel like I'm going to do a little bit of a shift in notation here, right? So what I should be doing is calling these T's. Just making sure I don't mess myself up for the rest of this lecture here. All right, let's call these T's. Here, so this H is basically, when you see an H, we're talking about some model, okay? And so let's suppose that the observations that I see are some true model applied to the inputs plus some noise, right? And this noise is, again, my usual, Gaussian noise. So if this axis is x and this axis is t, and we're just doing like one dimension, then my data points are going to look like, something like this, right? I'm going to be a little bit off from my curve. Okay. So now I'm going to think about applying linear regression just with a polynomial to this set of points, right? So let's suppose that I just do a straight line fit, right? That's like saying my hypothesis for the model is constant plus linear term times x, right? Well, what I probably would get would be a function like this, right? So here, this is like saying, the best linear fit. That's like saying, W0 plus W1x, okay? So this does not do a good job of fitting the data points that I have, right? Why does it not do a good job? Because the model is not complicated enough to represent what's going on in the data, right? So it doesn't matter how much data I had, my linear fit is still not going to go through the points because the points don't come from a line, right? So this means that this model is underfitting the data, okay? So even if there was no noise at all and an infinite number of points, the model still wouldn't be a good fit, okay? So let me write that down. So kind of linear regression which is the blue line, basically underfits the data. Right? No matter how much we have or how small the noise is. Right? So we're going to kind of quantify this idea, which is kind of like in the absolute best of worlds, how well could the model fit the data? And we're going to call that the bias. Okay? So we define the bias is basically the bias of a model is the basically test error even if we had an infinitely large training set. Right? So in this case, we would say that the linear model has high bias, right? Because even if I gave you a million noiseless points, I would still have a high error, right? So in this case, the straight line model has high bias. Okay? Okay. So now let's try to fit a higher order model, right? So now let's try to use maybe a, well, I've got a bunch of points here. Let's suppose I'm fitting like a, 8th degree polynomial, right? So here, let me draw, some other kind of fancy curve, right? So let's suppose here, this is like the best, whatever, 8th degree polynomial. Okay, so it definitely has less error, right, for sure. But this model has a different problem, and this is a problem we talked about before, which is that it doesn't generalize well, right? If I change the actual input data points, I may still have a low error, but I'm going to have a different curve, right? Because it's very sensitive to where those data points are, right? So let me write that down. So a higher order model say, 8th degree polynomial, has a different problem. And one way of thinking about that is it overfits the data. And doesn't generalize. So this model would have very low bias, right? Because actually, if the underlying model is quadratic, well, I know that this 8th degree family of polynomials includes all quadratics, right? So in theory, the bias for the model is basically 0 because the model can fit the data exactly. If I saw a bazillion observations, then the model would be great at finding this quadratic, right? But, so it has low bias, but has what we call high variance. And what that means is that fitting the model is very sensitive to the observation noise epsilon, right? So basically, if I had different noise, then I would have totally different, polynomials. So this variance is kind of, it's like the variance of the Gaussian, but this is like the variance of the model, right? In a way, what this is saying is that, we can measure the amount of variation that we would expect if we train the model on different sets of data, right? So basically, in this case, model variance, we can quantify by saying we measure the amount of variation we'd expect on models trained on different input data sets from the same distribution. Right? We would like to think that if I picked 10 points from this quadratic and fit the polynomial, and then I picked another random 10 points from the quadratic and I fit the polynomial again, but I should get the same thing, right? The variance measures how far away, or what is the spread of unpredictability in my output, right? And so kind of what we want, of course, is that both the bias and the variance are small, right? And what we're going to try to show, I'm not going to prove what I'm about to say, but I'm going to tell you this critical result. And the idea is to say that the error in a given model can be represented as basically the sum of a bias term and a variance term. So we can kind of decompose the overall error into a part that is attributable to how well the model can do in a raw sense, and a part that is basically how sensitive is the model to the random draw of observations that I had. And that's kind of what makes up the mean squared error. So we'll show, or we can prove, I'm not going to actually prove it, we can prove that the mean squared error for regression, which is what we've been talking about, can be kind of split into a bias term plus a variance term, which is sometimes a kind of an instructive way of thinking about your model, right? So I'm going to make this a little bit more mathematical without actually proving the math, but I'm going to just kind of try to quantify what I said in terms of just, instead of saying it in words, let me say it in equations, right? So here's the setup. Right? We are going to, draw a training set. Let's call it S, which is a, set of, input-output pairs, so that the output is some ideal model plus noise. And the noise is distributed, according to some IID Gaussian distribution, okay? So now I've got my random draw of data, and I'm going to train my model on this set S. So train a model on S. Resulting in, the model for that data, okay? And now I'm going to take a new sample from the same distribution. So take a new sample. This is not one of my training data points. This is just like a new, kind of version of sampling from the same distribution, and measure the expected test error. Right? And again, the expected value is kind of averaged across the random draw from S and the random draw from epsilon, right? So this mean squared error is basically the expected value over how I sampled and the point and the noise of my t minus the model of S applied to X. Right? So the noise is random, the set of points I found was random, and this is basically saying, now I give you one new sample, what do I expect the mean squared error for that one data point to be according to the model that you constructed, okay? So now the bias variance, trade-off theorem tells me that this number can be written as a sum of three things, okay? So let me write this down. So the key result is that, the key result is that the mean squared error at X is the sum of three things, right? The first one is sigma squared. Remember, sigma squared is the error that was in the observations in the first place, right? So it kind of stands to reason that I can never do any better than the sigma squared because there's always noise in my data, and the noise here is that's how much is added according to my setup, right? So this part here is just unavoidable because of the way that the data is constructed. Then I'm going to have one term that looks like this. And this is going to be a little bit of a hairy equation. So I have h star of X minus h, what I'm calling h average of X. So let me write this down first, and I'll kind of write down what it means. Okay, so this thing here is what we're going to call the bias squared, and this thing here is what we're going to call the model variance. And so let me explain what I mean here. So the bias term is basically saying, okay, how far off am I between the ideal model and kind of like the average of what the best that this thing can do, right? So again, kind of think back to the straight line example, right? This is like saying, how well could the best straight line over all possible data ever fit the true quadratic function, right? So this is kind of like saying, what is the kind of innate modeling capacity of the parameters of this model, right? So here, let me write down a little bit. So the bias involves this kind of like what's called h average of X, which is kind of like the best possible model with kind of infinite data. Right? It kind of tells us how well could we ever hope to approximate the ideal model, right? And the variance basically, a different way of looking at this is like saying, what is the expected value between the average model trained at X and the thing that I see, right? So this is kind of like just the variance from the mean, right? I'm going to move this over just slightly. So the variance basically measures how sensitive the model is to the randomness of the data set. Right? So usually as the data set gets bigger, the variance will get smaller. And this is kind of a nice way of thinking about how the mean squared error is composed of these two terms, okay? Now I know this is a little bit hairy, a little bit weird to look at. And again, this is something that maybe you want to go back and read the book section on the bias variance trade-off to understand this a little bit better, right? But kind of what I want to, draw a picture of is like saying, okay, so typically what you have in a model, right, is something like this, where, the complexity of the model I can kind of write on this axis, and the mean squared error I can kind of put on this axis. And kind of what you expect to see is that, the more complicated the model gets, the bias will get lower, right? So as the model gets more complex, the, bias squared gets lower, right? As the model gets more complex and there are more parameters to fit, the variance gets higher. So kind of like the variance, here gets higher. And the mean squared error, you can kind of think about like the sum of these terms, which hopefully when you fit your, model here, this is like the bias squared plus variance. You can kind of say, oh, this is the point where I'm trading off the, variance and the bias for a given model, right? So in general, the best model is a trade-off between simplicity and generalization, right? You can't get both at the same time. You can just try to do a good balance between the two, okay? And so on the homework, this is not exactly the same thing, but on the homework, I'm kind of asking you to, so one way to think about this is kind of like, I want to travel along this axis to find the best model. And what I'm asking you to do on the homework is to kind of apply a model selection criterion to the Gaussian mixture model, right? Because, the more Gaussians I fit to a data set, well, the better that I can do, but the more complicated the model is getting, right? So this BIC criterion, the Bayesian information criterion, is kind of one way of thinking about how do I penalize that, right? It's not exactly the same as this, but it's related to the idea, okay? And so again, I'm not I shouldn't say this because I'm teaching the machine learning class. I'm not like a machine learning expert, but what you do see in practice sometimes is that if you have a model that has a massive number of parameters and a massive amount of data, kind of, in practice, for models with many more parameters than data points, we kind of often see something like this, where, again, this axis is like the number of parameters of the model. This axis is the test error. And, kind of like in the classical world, you kind of expect to see something like this, right? Where there's like a little bit of a dip and there's a sweet spot where that's where you should choose your model. So kind of like here in the low, data regime, this is kind of like saying this is like the classical bias variance trade-off. But heuristically, models have billions of parameters, right? And so kind of what happens in practice is that at some point, even though you might say, well, I might stop with 5 parameters, if you kept on adding parameters, your test error can go like way down, right? So here, this is kind of like the world of modern over-parameterization. And there are tons of rules of thumb and tips and tricks for getting your network to have this behavior. So sometimes you see this called the double descent phenomenon. Which again, not a critical thing for our class, just kind of to give you some sense that there is some intuition that classical machine learning gives you from just basics of regression, and there's some stuff that happens in practice that comes from tuning these massive billions of parameter models that people just see happening, right? So again, when you're looking at a real world model, you may find this kind of behavior having to do with the number of parameters that you add to the model. Because it's kind of like one of these kind of meta-tuning things where it's like, okay, well, what should the number of parameters of my model be? Well, I'm going to kind of see what the test error is, and I'm going to evaluate, and I'm going to stop at a certain point where I get good performance, right? Okay. So, questions or comments? I know that probably this is like, oh, you know, what is he talking about? But so this is something to go back and take a look at more carefully, right? This is a little bit more machine learning theory than, you know, hands on the ground practice. So I want to tell you two more things, right? So one thing is that, you know, linear regression, the way I said it, I think that it's important that you know that, you know, linear regression, kind of no matter what your basis functions are, by itself is, you know, sensitive to what are called outliers, right? So outliers are basically data that doesn't fit the model. So just as a change of pace, let me show you some MATLAB. So let's go over to my notebook here. So here, I just made a little demo of linear regression. Wow, I fit some points, right? So very simple. I took 500 points. I sampled them along this true, you know, line, which you can kind of see from the picture. The red line is actually the linear regression fit, right? So you can see that when everything is like normally distributed, that my linear regression fit is exactly what I think it should be. Goes through the points, right? Now, if I add some outliers, right? So let's suppose I add 25 extra points that are not in the data set, right? That are a little bit farther off. Those 25 points are drawn from a different distribution, and they throw the linear regression estimate way off, right? And this is not so great, right? Because I want my estimate to be more robust to these points, right? And of course, you know, it doesn't actually take, you know, too many points. If I just use like 5 points, you know, you can already see these 5 points are torquing the straight line fit well away from the truth, right? These 5 numbers have a disproportionate effect on what the other 500 numbers are telling us, right? And of course, you know, it gets even worse, right? So there is an algorithm that will let you kind of, so let's go back to like the 25 example. So there's an algorithm that you can apply to try to address that problem. And there are actually many algorithms to kind of solve this issue of outliers disproportionately affecting the fit. So one way, and there are many ways of doing this, one way of several to, you know, combat this problem of outliers is called RANSAC, which stands for Random Sample Consensus. And the idea is super easy, right? So I'm just going to make a quick, you know, note of what it is here. So basically the idea is, you know, select a random subset of the data, right? And that random subset, you know, could be as small as the minimum number of points needed to fit the line, right? So I could say, okay, I'm going to just pick a subset of 2 points. In practice, maybe you'd pick a subset in this case of like, you know, 10 points or 20 points, right? So then, given that smaller subset, I fit my model to the subset, and then I calculate my errors, and I basically, you know, threshold that error to decide what points are inliers and what points are outliers, right? And then I basically pick the model with, you know, the most inliers, more or less. Kind of, you know, I do this some number of times, right? So basically it's like saying, you know, I take my data, I draw a smaller subset, I fit my model, and I see, okay, which of you points is close to this model, which is not, right? I keep on doing that, and then at the end I choose the best one, right? And so for you probability people, one way of thinking about this is I could have a probability problem on an exam that would be exactly like this. Where I could say, okay, I have a probability that a point is an inlier versus an outlier, right? So I can say, okay, here in this case, my probability of outlier is 25 over 525, right? And now I could ask, what is the probability that a random sample of 10 points contains no outliers? You could compute that like a binomial distribution, more or less. And then I could say, okay, what's the, how many sets do I need to sample to be 98% sure that one of those sets is all inliers, right? All I need is one successful all inlier set to get the right answer, right? So you could solve that as a paper and pencil problem, right? So here, if I apply the Rensselaer algorithm, what I see is this, right? So here, the Rensselaer fit is the green line, which is exactly what I want, right? So Rensselaer doesn't let those red points boss me around. And what I'm doing here is I'm coloring in the inliers and outliers according to the Rensselaer model. So Rensselaer thinks that all the red points are outliers and all the blue points are inliers, right? And you can see that, this will do pretty well. Even if I like crank up the number of, outliers, I can still get a great fit with my linear model, right? So this is something to kind of be aware of in real world machine learning. I will say that, there's this whole process of, outlier rejection, and retraining your model without the outliers. My understanding from machine learning practice is that, this is kind of more of a statistics problem where you're kind of like trying to explicitly assign inliers and outliers to the data points. But it's a good thing to have in your back pocket. Like I know about this from computer vision, which is basically, I'm often fitting some sort of a parametric model to some data. And if I'm clicking on like correspondences between points, a lot of times correspondences that may come up with like the SIFT algorithm or something like that, most of them are good, but a couple of them are bad. And those bad ones can throw off my model significantly. So in computer vision, we're kind of used to doing this outlier rejection process. And it's also a good thing to know about for machine learning. And the last kind of thing that I'll show you, which is a little bit fun, as another application, is kind of a fun, not exactly machine learning, but still the same kind of thing, application is what's called fitting a thin plate spline. It does sound fun, doesn't it? Let me just say that the setup basically, again, this is something that I assign in my computer vision for visual effects class, right? But I'm basically using linear regression with a certain kind of basis function to do it, right? So the setup is that I have, n image to image correspondences, right? I have basically, I click a point in image 1, and I have a corresponding point in image 2, and I do that n times. And then I have a model, right? My model is that the x prime location is got these basis functions, right? So here, this phi is based on the radius, which is like the distance between a point and point I. So again, don't worry about this. This is definitely off the beaten path, right? Kind of what I'm saying here is that I have a model that contains kind of like, you can think about this like the bias and these things as like linear terms. And then here, I have a whole bunch of other radial basis functions. And I do the same thing for y, ... So basically I have like, n plus 3, 2n plus 3 model parameters. So I have this kind of like, function of how to push points from image 1 over to image 2. And this is kind of like the fundamental theory of how you would do like image morphing, right? So image morphing is like one of the fun assignments that we do. So it's like saying you as the user, you click on a whole bunch of points over here in image 1 and a whole bunch of corresponding points over here in image 2, and then you want to know like where does this point go over here in this image. So here's an example with a toy car. Come on, I said example. Page down. Okay, so here's my car. Here's another view of the car, right? So what I could do is I could click on points here and click on points here. Those are like kind of lined up correspondences between the same points from different points of view. And then I could learn my model for how to push points over from image 1 over to image 2. And I could take this grid and I could push that grid over to image 2. And that you can kind of see that I've learned this nonlinear warping. So the radial basis functions are not like a, just like a rotation translation of the image. There's actually something definitely highly nonlinear going on here that comes from how far away each of the points is from each of those green dots. And then I can kind of say, okay, I can, what happened? I can then take like, I can then say, okay, I'm going to take all the points from image 1 and I'm going to push them over. And kind of what you're seeing here is this is the original image 2, and this is like the points in image 1 that are moved over to image 2. So it looks like the same geometry, but the picture is a little bit off because it's not very sharp. This is the sharp picture in image 2. This is like the warped image 1. The reason I want to do this is that if I do this between different views of different objects, right? Like kind of click on these points and these corresponding points, then I could do something fun like make halfway points between the two cars, right? So I can kind of use this warped displacement field to build this kind of morph. Like if you know morphing videos and visual effects, this is kind of like how they do it, right? And so what's under the hood of this is purely a radial basis function type of regression that you'd solve with this big phi transpose phi inverse matrix, right? That's like one of my homework assignments in this other class, right? So just to give you some sense of that, this is not maybe like a traditional regression problem, but it is solved using the same way, right? So if you're curious about this, you can read more about it. Generally, you could learn more about what's called scatter data interpolation, which is kind of like what this is. And you can watch my morphing video on YouTube if you want to learn more about the way you set it up. Okay. Any final questions or comments? With that, I will see you next time.